In our discussion of mixtures, so far we've taken a macroscopic approach for understanding, how molar volume, enthalpy, free energy, how those things are affected by changes in the mixture composition. But when it comes to entropy, it's also very useful to also take a molecular approach for understanding how changes in composition will affect the total entropy of the system. And so when we were looking at the ideal gas, we saw that our entropy of mixing for the ideal gas was equal to minus R summation of I is equal to 1 for all components yi ln of yi. Okay? That's just what we derived for the entropy of mixing for an ideal gas. We'll see soon that even if we're not dealing with gases, if we're dealing with liquids or solids, we'll also see that delta S mix will be equal to minus R summation summation of xi ln of xi. Okay? Now this front xi term, that comes from the fact that we have to directly multiplied our entropy terms by like moles, and then we divide it out by moles. But it doesn't explain why we have a natural log of the composition as well. But in any case, I want to highlight that this term, this minus R natural log xi term, is actually somewhat universal. And the reason it's there, the reason it keeps showing up in all of our equations, it's because it's describing the number of ways that we can arrange molecules in a mixture. Okay? And as you know, in order for a system to be at equilibrium, it has to reach a state where its entropy is maximized. Okay? And so the system will arrange itself in a way that it maximizes the number of ways that the molecules can arrange themselves. The more technical term for this, or the way we refer to it, is we refer to it as translational entropy. Number of different ways a molecule can arrange itself. All right, to get a better handle of how the entropy is affected in a mixture, what I want you to consider is a mixture of A and B molecules arranged on a checkerboard. Okay? Alright, so picture in your mind a checkerboard that looks like this. Okay? And on this checkerboard, there's a certain number of squares. I think we have 5 by 5, so there's 25 squares. And we'll let the number of squares, or the number of sites in our checkerboard, be equal to n. Okay? And so, if we have a mixture of A and B molecules, let's say we arrange the molecules like this. So, let's say we have A molecules here, 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 and here. And then the B molecules would be like here, 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 here. And let's add some more A molecules for good measure. Okay? All right, and so we have, a total of 25 different molecules, and they fill up each of the different sites. But the picture we're looking at now, this is only one possible combination of how we can arrange the molecules. Right? And another instance, or another conceivable instance, let's say we just kind of switch the places of some of the red and blue molecules, right? And so that's another possible configuration of how we could arrange the molecules in our system, okay? And so tying back to what we saw in chapter 5.5, right? The different ways we can arrange the molecules in our system, that's known as the multiplicity. So, and if we particularly look at just the way we could arrange species B, molecules, we could call that omega B. All right? And we saw, back in chapter 5.5, that to describe the multiplicity, this multiplicity was proportional to this formula, where we have the total number of places that are available to put molecules, so total number of sites, n, and that's raised to the number of B molecules that we have, and then that's going to be divided by the factorial of n B molecules. All right. And so that's, the sort of equation that we, derived back in chapter 5.5 in order to calculate or estimate the number of ways that molecules can arrange themselves in the system. Okay? To be a little bit more precise about this, we could play around, with these factorials by applying Stirling's approximation. And Stirling's approximation was just saying that natural log of some n factorial could be written in this form. Minus nb. Okay? If we took the exponential of both sides, we could also write it in this form, where we have nb divided by e, and this is all raised to the nb. Okay? So that's just a way to rearrange Stirling's approximation. So if we go back to our omega formula and plug that approximation in, we get that omega b is now equal to n over nb times e raised to the nb. Okay, so that's the multiplicity of B. That's the number of different ways we could arrange the B molecules in our checkerboard mixture. And then we could use the microscopic definition of entropy, which was K ln of omega. And we could plug in our omega equation here. Okay? And so, I'm writing that this is proportional to, but all the other stuff I'm not writing here is stuff that's not going to depend on MB. All right, so we're just not going to worry about it for now. In any case, so our SB is going to be proportional to K natural log of N E NB raised to the NB. If we play along with our log rules, we could bring this NB exponent down to the outside, and we could also split up the natural logs here. Okay? So for this first natural log, I'm going to write it like this, and it's negative because NB and N positions were flipped originally, so I flipped them around. So we have this. And then I'm going to split off the natural log of E thing over here. Okay? Now the reason I wrote it in this format is this natural log of E, that's just 1. So that's simple. And over here, what we have is the number of B molecules over N, or the total number of molecules in our mixture. And so if we have NB over total molecules, that's just equal to a mole fraction. Okay. All right. And so this is our functional form of SB for now. But, we're dealing with mixtures, and in the previous videos you saw that the partial molar quantities of mixtures are very important. And so what we could do now is we could calculate the partial molar quantity of molecules B. By definition, that's just DSB divided by DNB at constant T, pressure, and constant A. Alright, and so if we apply this derivative, this partial derivative, we'd be differentiating this. Plus 1. Okay. Out here, this is written as total molecules of B rather than moles. But we know that the total molecules in a system is just going to be equal to Avogadro's number times the moles of that system. The moles of that species, right? So this is Avogadro's number. Okay? And so our partial molar quantity SB is going to be equal to KB, Avogadro's number. And what I'm going to do, since we're taking the derivative with respect to NB, I should also mention that this mole fraction is also just NB over NA plus NB. So when we're taking the derivative, we have two instances of NB, or three, that we need to worry about. Okay? So let's perform the derivative, and here's the result that we get. Minus ln of xb plus 1, and then plus nb minus 1 over nb plus 1 over na plus nb. Okay? If we multiply this by this, we'll end up with negative 1. And that will cancel out with the positive 1 that we have here. And if we distribute across NB on top of this, we get NB over total moles. And so that will give us back another mole fraction. Plus RXB. Okay. And so we see that the partial molar entropy of species B has this functional form. And now that we're here, I'm going to make one last assumption. Let's say that we're dealing with a dilute mixture of B, such that the mole fraction of B is very small. If we're dealing something where XB is very small, this term right here is going to be basically 0. Okay? And so what we'll get is that SB is going to be equal to minus R natural log of XB. Okay? And so from a molecular perspective, we could still reason out, find a way why this sort of term keeps popping up whenever we look at the entropy of mixing. Right? And so what the entropy of mixing is describing is just, the number of different ways you could arrange the molecules within your mixture.